Hey, welcome. So my name is Steve Miller. As was mentioned, I'm a professor at Williams College, and I want to talk a little bit about Benford's law, which surfaces in a variety of places, and in fact, it may be in the news in the near future in America for reasons that will become clear soon. It is about the prevalence of certain digits. So in many data sets, you see certain numbers more frequently than you would have expected. This talk is the third attempt to give this talk here, and I hope in the near future to be able to fly out and give a different talk on related issues. The other thing I want to quickly mention is I'm the director of the Williams College Summer Research Experience for Undergraduates program, as well as one of the founding members of a polymath REU, where we are trying to provide as many opportunities as possible for students. And so for those of you in the audience, either students or professors, if you are interested in summer research, please let me know. My email address is on the page here. If you're interested in helping us come up with some problems or maybe even running a group, there will be stuff being done remotely, so we can have people all over the world, and we are always looking for additional people. Okay, so first, all the slides will be available. There's just a couple of books that have now been written on Benford's law and all of the different applications. So what is the motivating question? What is the reason why so many people are interested in this? Well, if you look at a lot of different data sets, Fibonacci numbers, and you might be able to see my shirt, Fibonacci numbers is as easy as 1123. Stock prices, street addresses, college employees and students. You could look at each number and pull off the first digit and ask what fraction have a first digit 1, what fraction have a first digit 2 or 3, and so on. And you might guess initially everything should be equally likely, so maybe around 10% for everything. And he goes, oh wait, no, it's not going to start off with a 0, because if we're looking at the first digit, 0.003 would have a first digit of 3, so there's really only 9 possibilities, so you might correct to 11%. It turns out, in fact, it's very different. And in fact, base 10, about 30% of the time, you have a first digit of 1, and it declines in probability all the way down to about 4.5% of the time with a first digit of 9. Just as a remark, for those of you who have your faces showing, this is wonderful. I actually get to see faces. I don't know if, Aaliyah, if your Zoom recording records people's faces. So if you have your video on, please try to look interested. So here is a couple of different data sets so that you have some idea that this bias is in many, many settings. So the first is the Fibonacci numbers, and we'll actually prove why that is the case. Twitter uses by the number of followers. The most common iPhone passcodes, I would prefer not to say how I got that data. And then distances of stars from the Earth. And you see, it's not the same in all of them, but you can see this prevalence towards having the first digit being a 1 or a 2. So for the talk today, I want to explain a little bit about Benford's law. I want to talk about some examples and some applications. It's often used to detect fraud, and that is an extremely valuable application. I'm going to sketch a couple of proofs, and then as time permits, I'll talk a little bit about some open problems. If you are looking at all the little dots at the top of the slides as to how many pages there is far more stuff here than I'm planning on doing. This is a highly modular talk, so depending on what your questions are or what you're interested in, we can go into different routes. Or if you want to see more details, I'm going to skip over some of the technical slides and you can go back and look at those later. The first thing, though, is a little bit of a warning. A math test indicating fraud is not proof that fraud happened. Unlikely events can occur, and there can be alternate reasons. So I actually emailed Scott Adams for permission to use this comic strip, and he was kind enough to allow me to use it. So Dilbert's travel expenses, in the old days you actually used to get to travel to places, are rejected because all of the meal costs are round numbers, and Catbert, the evil director of HR, says you are a liar or worse. And Dilbert responds, I decide what to order based on what totals a round number after 15% tip. And Kappa goes, that's worse. It is important to remember this because there's a huge desire to use Benford's law as a cure-all to, fraud has happened, look what we have seen. And right now we are about to have lots of claims of fraud happening. Some of the claims are going to be true. I have heard places had more than 100% turnout. If you have more than 100% turnout, it's pretty clear that something happened. But there's a lot of rumors going on the internet right now and social media, which have been debunked. And so it's very important when you are developing tools that you know when is it right to use this tool. So here's a couple of examples where Benford's law has been shown to hold. Occurrence relations And these are discrete forms of differential equations, which gives you an idea of why it might be so prevalent. Special functions like n factorial, iterations of power exponential rational maps, products of random variables, for the number theorists in the room, L functions, the 3x plus 1 map, lots of different places. For the statisticians, many hierarchical Bayesian models. So there's lots of different places. What I love about the subject is you have people all over the academic spectrum who are interested in studying problems like this. So 3 big applications. The first is analyzing round-off errors in how computers store information. The next is determining optimal ways to store numbers. And then the most interesting is detecting tax and image fraud. And so one of my colleagues, Mark Negrini, is the one who pioneered using Benford's law to detect tax fraud. On an individual tax return, there's not enough data to indicate whether or not an individual is cheating. However, if you amalgamate across the entire population, it becomes extremely likely that on a whole, people are lying on their taxes in certain categories. Charitable donations is one that's usually given as the example. How much was it worth that you gave? And a lot of nice round numbers emerge as those are being filled out. All right, so let me talk a little bit about the general theory. So for many data sets, the probability of observing a first digit of d base b is the log of d plus 1 over d base b. So base 10, about 30% of the numbers are going to start off with a 1. So we don't actually need too much mathematical background to do a lot of the analysis. The first is basic modular arithmetic. So we say a equals b mod c if a minus b is an integer times c. So 17 would be 5 mod 12, and 4.5 would be 0.5 mod 1. We will mostly be doing modular arithmetic with 1 because we will only care about the fractional parts of numbers. The next is writing things in scientific notation. Some people sometimes use the word mantissa. I have been told you're supposed to use the word significand. So we write x as the significand of x times 10 to the k. K will always be an integer. It'll be basically where's the decimal point, and then the significand will be a number between 1 and 10. And then 2 numbers will have the same significand if and only if they have the same leading digits. And what's nice is if you take the log base 10, then their logs will differ by an integer. So the fractional parts of their logarithms will be the same. And in fact, this gives you an idea of why Fourier analysis plays such a key role. Normally, you can't just throw away the integer part of a number, feed it into a function, and get the same value as before. But if we're looking at e to the 2 pi I u, well, that's the same as e to the 2 pi I u mod 1. And this is a sense of why it's better to take our data, do a logarithmic transform, and now the tools of Fourier analysis are applicable. And we only need to look at things modulo 1, and you can see the Fourier series coming into play. So the first thing we'll need is the notion of equidistribution, or uniformly distributed, or evenly distributed. So we say a sequence is equidistributed mod 1 if the probability mod 1 that it lies in the interval AB converges to B minus A. So explicitly, we count all the way up to some number big N and see what fraction of the time we're in the interval AB, so we divide by N, and that should converge to B minus A. One of the big tools is that if beta is an irrational number, then N times beta is equidistributed mod 1. And there's lots of ways to prove this. That would be a separate talk. I will just give 2 examples of numbers that are irrational that will be useful in the talk. The first is the log of 2 base 10, and the second is the log of the golden mean. And so since every talk should have a proof, I will prove that the log of 2 base 10 is irrational. If it was rational, then we could write 2 as 10 to the p over q, or we could raise both sides to the qth power. 10 is 2 times 5, so we get 2 to the q minus p equals 5 to the p, and this is impossible. Right. So let's look at the equidistribution. So the square root of pi is irrational. So if we look at n root pi mod 1, that should be distributed uniformly as we look at larger and larger ranges. And what I like about the square root of pi is the data looks pretty good when we only look at 10, but it's not perfect. I have nothing in this bin from 0.2 to 0.3 and 2 things in that bin. If I bump it up and look at up to 100, we can see it looks pretty good, reasonable sized fluctuations. Up to 1,000, the fluctuations are getting smaller. Up to 10,000, you need to have really good vision now to see the little bit of dips and whatnot. It turns out you can quantify how quickly n root pi becomes equidistributed, or in general, n times beta becomes equidistributed, it comes down to how well can you approximate your number beta by rationals. And that part of algebraic number theory comes into play in a lot of these convergence. And this is extremely important for applications. If you're trying to detect fraud, the big question is, well, how many data points do I need before I can say something suspicious is happening? Do I need 1 million data points, or is 100 enough? So the fundamental equivalence, we've already hinted at this, is to do a logarithmic transformation. So a data set xi is Benford if and only if the logarithms are equidistributed mod 1. And to see this, we write x as its significand times 10 to the k. So when we take its log mod 1, we get the log of the significand mod 1, and that'll be a number between 0 and 1. So if we just look at it, here's x, the significand ranges from 1 to 10. Here's the log of x, ranging from 0 to 1. So if you have a first digit of 1, then you're between 1 and 2. And so when we take the logarithms, you're now between 0 and the log of 2 base 10, which is about 0.3. And this is where the bias is coming from. If you are equidistributed over here on the log side, you will have a bias up here. So Benford's law actually vanishes if you do a logarithmic transformation and look at the log of data. Now, if you have real world data, sometimes you can do that and it's still meaningful to talk about. I don't think we want to be talking about the log in Celsius of the temperature or the log of a batting average of a baseball team. The numbers have a nice meaning. And so we do see the Benford's law and the digit bias, but if we take logarithms, it vanishes. And then as a quick check, you can just see that if you sum all the probabilities, it's going to sum up to 1. And so if we can prove that the log process is uniformly distributed, then the original underlying process is going to be Benford. The hardest part is finding the right way to look at things. So I like to do a lot of stuff with Rubik's cubes. I'm not going to risk actually showing the cube over here. Here are 2 cubes that look very different. And if you look at this cube, it's got a much stranger shape in places. It turns out the 2 cubes are equivalent. The blue side over here is not the same as the blue side over here. You can't physically turn this blue side clockwise or counterclockwise. It turns out that the side that corresponds to the top over here would be these 3 pieces coming down like this. This whole thing here I can turn around clockwise. This cube is really the same as this cube if you just rotate it 45 degrees and hold it at an angle at a wedge. And so much of the stuff on Benford's law is just trying to find the right way to look at what we have. So let's look at some examples. So let's look at powers of 2. So because the log of 2 is irrational, base 10, it should be Benford. Fibonacci numbers should be Benford as well. And the proof is the following. So we start off with the fundamental recurrence relation for the Fibonacci's. Each one is the sum of the previous 2. And so we guess that the nth Fibonacci number is of the form r to the n. We quickly get that if that's true, then r squared equals r plus 1. So we get 2 roots, 1 plus or minus root 5 over 2. If that works, we could multiply by any constant and it would work. Because it's linear, we could sum 2 solutions and it would be a solution. And so the general solution is of the form C1R1 to the n plus C2R2 to the n. This is Binet's formula. And so we just figure out what the values of C1 and C2 are from the initial conditions. So A0 is 0, A1 is 1, and we get the following. Because 1 minus root 5 over 2 is less than 1 in absolute value, as n gets very, very large, this number just goes to 0. So you have to do a little bit of bookkeeping, but essentially the nth Fibonacci number is 1 over root 5 times the golden mean to the n. When we take the logarithm, well, the log of 1 over root 5, that's just a fixed constant shift, and we get n times the log of the golden mean. And since the golden mean has an irrational log, we know that n times the log of the golden mean is equidistributed. So when we exponentiate, we get Benford. So the Fibonacci numbers are Benford with just a little bit of bookkeeping for this. Most linear recurrence relations actually turn out to be Benford. If I give you an plus 1 equals 2an, that's our doubling sequence, the 2 to the n, that's Benford. If, however, I gave you 2 to the n, 2an minus 1, that would not be Benford. And so if I take a0 equals a1 equals 1, I actually get every term in the sequence as 1. If I take a0 is 0 and a1 is 1, I actually get 1, 2, 3, 4, 5, I get the integers. And what's going on here is we have a double root in the recurrence relation, and both roots are 1. And so we're not going to have an irrational log. Okay. So earlier I mentioned the big question is, well, how many data points do we need for Benford to set in? So I looked at the first 60 values of 2 to the n. Because the numbers are getting quite large, I'm only displaying the first 30. And so, here's the first 60 over here. And for each digit, I count how many times do I observe the first digit being 1, 2, 3. I look at the observed probabilities versus the Benford probabilities. Which digit do you think looks the worst? One looks pretty good. Anyone strike your fancy as suspiciously off? Yes. Clifton, I can't see what you said. 2?
Yeah, I just held up 2 fingers.
Okay, so you think digit 2
but I
is
think
the one that's the worst? Why digit 2?
Well, the difference from the Benford probability looks a little bad, but
So this is good because I'm getting lots of numbers. So I've got 2, 8, 3, 4, 5, 9. So far 7 hasn't been hit, 6 hasn't been hit. Okay, I see why 6 hasn't been hit. 6 is pretty good. So it's an interesting question as to how do you want to decide which one is the worst? So one is you could look at the absolute magnitude of the difference between the observed and the Benford probabilities. You could also look at the relative difference. If you divide them, what is the multiplication factor? And if you do that, I think 9 would come out as the worst.
9, yeah.
In terms of just how much it's off by. But the problem is we have a small data set. And if you look at it, what's really going on is 2 to the 10th is 1,024, which is almost 1,000. So you are in the part of the world that does the metric system, right? Okay, so we're still in the English system, but I think we all agree on some things, such as how many megabytes are in a gigabyte. So in computer science, it's actually better to do 1,024 rather than 1,000 because the computers work base 2. Because 1,024 is almost 1,000, what this means is every 10 iterations, we almost return to where we started. And if you look over here, it's not a coincidence that I'm doing, 10, 10, 10. So you can see, oh, here's my 5s, and it really is staying in the 5s. It's going to be a while before this moves up to a 6. And in fact, in the first 30 numbers, we don't see any first digits of a 7 or an 8, I'm sorry, a 7 or a 9. It's going to be a long time before the 8 climbs up to high enough to give us the very first 9. So to just test things a little bit more, I chose 3 of my favorite numbers, the Euler-Mastroianni constant gamma, E, and pi. And what I did is I did a chi-squared test to see how close they are to Benford. And so the smaller the chi-squared value, the better the fit. And more, if it's a good fit, 95% of the time, it should be a value of 15.5 or less. And if you look, 2 of them seem very good. There's a little bit of fluctuation, it goes down, it goes up, but these numbers are pretty small. Same over here. And then for pi, it starts off really bad, and you go, okay, well, maybe it was just taking pi a little bit longer to converge. But then it shoots up again. And the numbers are getting smaller, but it's still much more sizable than the other 2. It's still a good fit, but it's not nearly as good of a fit. And so the question is, what's going on here? So do we have undergraduates in the audience? Are there any undergraduates who can rattle off digits of pi? Okay, so somebody's putting something in the chat. 3.14159, okay. Could people go further than that if needed? Without Googling or anything like that. Usually somebody knows, usually there's at least one person. There we go, all right, 3.14159265358. Okay, good. Okay, who can give me Ah, there we go. There we go. Now we're getting there. Okay, who can give me digits of pi squared without Googling? Who's memorized digits of pi squared? You stopped at pi? You didn't go further? Oh. Well, okay, now you at least have something to do later tonight. So what I've done here is I've plotted the chi-squared value. So again, the higher the value, the worse the fit. Red is going to be the chi-squared for pi to the n, and blue is going to be for e to the n. And as we saw, the values for pi to the n were not as good as e to the n. If you look at this, does anybody notice any patterns in the red? So what pattern do you notice? All right, something is in the chat. It looks like it's periodic-ish. I love the ish. Yes, periodic-ish. Its magnitude seems to be getting smaller. Does anybody want to guess on the period? And if you can't tell me exactly what the period is, can you give me a range for the period? So an upper bound or lower bound. All right, so somebody says 200 for the period, 200-ish. I think 200-ish is a little bit better than 200. Do you think it's as large as 200, or do you think it's a little smaller? Because over here comes a little bit smaller, comes down, comes up, comes down. So I'm seeing 180 to 200. Okay. So now I mentioned about digits of pi. If you calculate pi to the 175th power, you see that it's 1.0028 approximately times 10 to the 87. So every 175 times you iterate, it is almost the same as padding your number by 87 zeros. Not quite. And this is very different than 2 to the 10. 2 to the 10 was basically 1.024. This is essentially 1/10 of that in terms of where the changes. It's going to take longer for it to accumulate. And this is why the convergence is much slower for powers of pi than it is for powers of 2. It comes down to how you are approximated by rationals. Okay. I'm going to skip the next few slides. That's some work I did with some students a few summers ago. So I want to talk a little bit about why Benford's law. So I want to give a few heuristics. So the first is, imagine you have a long street and the houses are labeled 1, 2, 3 all the way up to L. Well, if you stop at the 199 house versus stopping at the 999 house, you're going to get a very different fraction of first digits of 1. In the first case, it's going to be very close to 5/9. In the last case, it's going to be very close to 1/9. And so you can plot what's going on, that as you increase L, what fraction of the houses have a first digit of 1. Well, we've been seeing that taking logarithms is good. So if I plot the first digit versus the log of the street length, looking a lot more periodic and nice. What if we had many streets of different lengths? And so one of the ways you see Benford's law is the more amalgamation you have, the more different processes you have, the more likely you are to have something Benford. So initially, let's assume we have 1,000 streets and each street has exactly 10,000 houses. Well, we're going to get a nice uniform distribution for the first digit and the first 2 digits. It's not going to be close to Benford. But what we could do now is we could look at, let's say we have 1,000 streets, and each one of them, we randomly choose a number uniformly from 1 to 10,000 for the street length. And now when we do this, it's a little bit closer to Benford. We could do this again. We could first, randomly choose a number from 1 to 10,000, and then randomly choose a number from 1 to whatever we just chose. And you can see it's getting even closer to Benford. And if we did it one more time, the fit's now becoming beautiful. And this is just meant to be an example that the more averaging you have, frequently the more Benford you become. So let me give another explanation as to why Benford shows up. This one is going to come from probability and the central limit theorem. So one of the reasons we love calculus, why we love taking areas under curves, is areas under curves correspond to probabilities. And so I want to calculate, what's the probability that I take on a value between A and B? Well, it's just going to be the area under the curve from A to B. And so the big idea is the central limit theorem, that if you have a bunch of independent, identically distributed random variables, then if you look at their average, so I sum all my random variables, I subtract n times the mean, I divide by sigma the square root of n. So this, standardizes something to have mean 0, variance 1, then this should converge to be normally distributed. Okay, so to just see this in practice, let's imagine we have a uniform random variable between -0.5 and 0.5, and then we'll adjust it a little bit to have mean 0, variance 1. And what we can do is we can plot it against a normal. And we see that if we have a uniform distribution versus a normal, it's not terrible, but it's not a great fit. If, however, we look at the sum of two uniforms and you adjust everything to have mean 0, variance 1 and compare that to a normal, that's actually not that bad. The triangle is not a terrible fit to the normal. If we have 4 of them, it's even better. If we have 8 of them, it's even better. Now, you could do things explicitly. So here's the explicit formula for the density of the sum of 4 normals. You do not want to see what it would be for the sum of 8. The font size would be terrible. We don't want to have to do calculations like this. This is why the central limit theorem is so wonderful, because it says, it's close enough, just approximate it with a Gaussian. And so what we want to do is, we know that everything we do for Benford, we always are looking at what happens modulo 1. We take the log and we look modulo 1. So if we have something that's normal with mean 0, variance sigma squared, what happens is the variance gets larger and larger and larger when we look at it in mod 1. That means we're basically wrapping it around. And so here I'm choosing the variance to be 0.01. So that means the standard deviation is 1/10. So if the mean is 0, 2 standard deviations goes up to about 0.2 or down to -0.2. -0.2 is really 0.8 to 1. So if you look at this plot, this is what's going on if I take the probability of Gaussian with variance 100th and look at it modulo 1. If I increase the variance to 0.1, we can see that the Gaussian is looking a lot closer to being uniformly distributed. If we increase the variance to 0.5, at first you might think it doesn't look uniformly distributed, but every graph should have a label. And if you look at the y-axis, you see we're going from 1.0001 down to 0.9999. So there's almost no fluctuation. It's essentially a uniform distribution. So a Gaussian with increasing variance, mod 1, is essentially a uniform distribution. And so now, whenever you see a product, you should always take a logarithm. So if we have a product of random variables, which a lot of things in the real world can be given as a product of random variables, if we take the logarithm, the log of a product is the sum of the logs. And so when we take the logarithm, we get a sum of logs. Well, if each one of these is an independent random variable, the sum of their logarithms is becoming normally distributed. And we want to look at this mod 1, and what we just saw is if you have a Gaussian with growing variance, when you look at it in mod 1, it becomes the uniform distribution. So Vn, which is the log of the product, is converging to a uniform distribution. So when we exponentiate it, we get Benford's law. And this is another way to see why Benford occurs in so many different settings. Okay, so applications. So there's many different Steve Millers. This is a Steve Miller who lost his job in the scandal IRS gate a few years ago for not using math to determine which should be audited. All right, so here's one of my favorite examples. There was an audit of a bank, and they looked at a lot of the transactions, and they saw there was a huge spike in things starting with a 4. And they looked a little bit further, and they saw there were a lot of 4 8s and 4 9s, and they traced a lot of this down to one person. And it turned out that these were basically 4,800, 4,900. And what was happening is this person had their friends apply for credit cards and went up debts below 5,000, and then call and report, my credit card's been stolen. I think people have been putting some charges on it. Oh, don't worry, you're not liable for any of the charges. And so the bank's policy was anything below 5,000, the agent could just write off without having to do any paperwork. This is a great example of why you should never have hard requirements of what can and cannot be investigated. When you are trying to screen people for the plane, a grandmother, elderly woman in a wheelchair, you have to screen some of them as well. Otherwise, you have just said this is a category that will not be checked carefully. What you could do is you could say anything above $6,000 is always investigated. Anything between $5,000 and $6,000 is investigated with a probability of 0.9. 3,000 to 5,000 with a probability of 0.7, something like that. For 15 bucks, you don't want to spend too much resources investigating $15 on a credit card. But 4,000, 5,000 might be worth it. And so this was a great application of Benford's law. For another example of fraud or whatnot, there is a cat hiding in this picture of a tree. It is extremely hard to see the cat in the tree. And so let me show you how to find the cat. So how do you transmit an image? So imagine we have an L by W grid, and each pixel is going to be a red, green, blue triple. And often we do up to 2 to the 8 minus 1 up to 255. And so that gives us 256 choices for each of the colors, or almost 17 million possibilities. My eyes are getting worse as I get older, but even in my prime, I couldn't see anywhere near 17 million different shades of color. 1,000 shades is even more than I can do. This gives us an interesting opportunity. So steganography is the act of concealing a message in another message. Take one of the colors red, and imagine we changed just the last digit. Then we'd only change the pixel color by at most 1. 1 out of 255, 256, that's a negligible change. And a lot of the times there'll be no change at all. If you wanted to take a regular text message and write in black letters on a white piece of paper, that's just zeros and ones. You can hide that message by just changing the red pixel. If you change the last 2 pixels, you now have 4 possibilities. And so if we do this for red, green, blue, there would be 64 possibilities. So that would actually give you 64 colors to work with. So where's the cat? The cat was done by just changing the last few digits of the pixels. And you might see that this image is not the sharpest image of a tree. And that's because we are losing a little bit of that. But we were able to hide the cat without too much trouble. Okay, so what I want to do now is I want to turn to some more interesting theoretical applications. And so I want to talk a little bit about some situations and some circumstances where you have Benford's law. So I'm just very quickly going through this. You can always hit pause or look at the slides. So we're going to say something is Benford good if the following conditions hold. So X is my data, Y is basically going to be like the log of my data. I want the CDF to be given by some nice function. Often it might be a Gaussian. I want to have small tails so I don't have too much probabilities in the limit. I want the Fourier transform to have some decay. And I want small translated errors when I'm looking at sums like this. So these are the technical conditions. And if something satisfies these processes, you can prove that the original data set will be Benford. And it's just a nice application of Fourier analysis and just error keeping. The difficulty is showing that your system satisfies these conditions, in particular the small translated errors. That's really the hard one. So if you look at the 3x plus 1, okay, so I was going to mention that. This is just the proof, which I will skip. Okay, so here is one situation where you can apply it. You can apply it to L functions, in particular to the values of L functions on the critical line real part of S equals 1. So here's the famous Riemann zeta function. It's the sum of 1 over n to the s, n ranges over the integers. This converges if the real part of s is greater than 1. What I love about this is there's really no mystery in the distribution of the integers. We actually even have a formula for the nth integer. It's just n. We know the spacings between adjacent integers. It's 1. But because, using the geometric series formula and unique factorization, because this is the same as the product over primes, the hope is you can pass from information over the integers to information over the primes. And there's many ways you can do this. If you take s equals 1, you get the harmonic series which diverges, which gives you that there must be infinitely many primes. If you take s equals 2, this is the Basel problem from Euler. The sum is 1 over n squared. It equals pi squared over 6. Pi squared is irrational. If there were only finitely many primes, this would be a rational product. So there must be infinitely many primes. So this is just the tip of the iceberg of the connections. And so in this plot, I have plotted, a little bit over 65,000 values of the Riemann zeta function moving up in steps of size 1/4 on the critical line. And I looked at how often was the value of the absolute value having a first digit of 1, 2, 3, and compared this with Benford's law, and it's a beautiful fit. And so we can actually prove that it is Benford not just for the Riemann zeta function, but for other L functions by showing that it's a Benford good process and dealing with stuff like this. The next one I want to talk about is the 3x plus 1 problem. There's a tremendous number of great quotes about this. Kakutani once described it as a Soviet conspiracy to slow down American mathematics, because every time he went and gave a talk on this, people said, oh, that's not too bad, and they would spend a month in frustration. The great Erdős has said mathematics is not yet ready for problems like this, which would give you a sense of just how bad this can be. And so the way it works is you take an odd number, you multiply by 3 and add 1, and then pull out as many powers of 2 as you can until you get a new odd number. And then you just lather, rinse, repeat. You keep doing this. And the conjecture is that no matter what number you start with, eventually you iterate to 1. And once you have 1, you just iterate back to 1 and just cycles forever, 1, 1, 1, 1, 1. So for example, if we start with 7, 7 goes to 21, 22. I divide by 2, I get 11. And I'm putting the 1 down here to say I've pulled out 1 power of 2. And just as you iterate like this, you can record all the powers of 2 that you do. And the 2 path would just be the first 2 numbers I pull out. The 5 path would be the first 5 numbers I pull out. More generally, the m path would be the first m. And what I was able to show with Alex Koncharovich is that he had proved in his thesis with Sinai at Princeton that the m paths converge to being independent geometric random variables. We proved if you look at where you are after m iterations and divide by where you expect to be, that's Benford. And then Jeff Ligarius and Sound proved actually something even better. They proved that you choose a small tolerance, almost all things are within that small tolerance of the Benford probabilities. And just to give you a little bit of sense of the data, I chose a random 10,000 digit number. It's very easy to work with numbers this large because all we're doing is we're adding, we're multiplying, we're dividing by 2. So if you write your number in base 2, it's just a very long string of zeros and ones, and you can do the operations very rapidly. And you can see beautiful agreement between Benford's law and the data. If you don't pull out all the powers of 2 at once, you could define the function that way as well, and you still have excellent agreement with Benford. All right, so I've got about 8 minutes left. And so for the last few minutes, I wanted to talk about a project I did a few years ago with some students and a colleague of mine in physics on stick decomposition. And there's a lot of different decomposition problems we've done. You can do more number theory ones where I take an integer and maybe I break it into primes or I break it into squares. Here we're going to just break it into fixed amounts. So the way it works is we consider a stick of length L. We uniformly choose a proportion P for all time. You could, of course, choose a different P each time. We were able to solve that as well, but for simplicity, let's just fix a probability P. And so we'll break the stick into 2 pieces. One will have length P times L and the other 1 minus P times L. And then we can repeat this n times using the same proportion each time. Again, you could generalize and have a different proportion each time. So here we start off with L, PL, 1 minus PL, and then P squared L, 2 P1 minus PLs, and a 1 minus P squared L. And initially, we conjectured that the decomposition process is always going to be Benford for any P other than P equals a half, because if P equals 1/2, then, well, all the proportions are the same, and at the nth level, you just have everything is just L over 2 to the n. And just as a test, we chose 0.51, 0.99, and you see beautiful agreement. Turns out the conjecture is false. And so if you take P equals 1 over 11, so 1 minus P is 10/11ths, it is quite off. So what's going on here? So there's some nice math behind it, and there's a really nice perspective as to how you handle this. So imagine at the nth level, we have 2 to the n sticks. So we can write the sticks, their lengths is P to the n minus j, 1 minus P to the j. That's the standard way of writing it. But I mentioned earlier that so much of the analysis of Benford's law, it's like the Rubik's Cube, is finding the right way to look at it. If you turn it to a 45-degree angle, you then see, that's really the blue face. The blue face is not the color blue. A better way to do this is to say, well, look, what's the J dependence? Every term has a P to the N. Let's just pull out the P to the N, and then we're left with 1 minus P over P to the J. Ah, this looks like it's a geometric series. The lengths are just 1 minus P over P times the previous. And now you might see where this 1 over 11 comes from. If I take 1 over 11, 1 minus 1 over 11 should be 10 elevenths. Divided by 1 11th would give us 10. So each stick length is 10 times the previous. So all of the stick lengths in this case will have the same first digit. So we see that the behavior as to whether or not it's Benford is going to depend on whether or not 1 minus P over P is 10 to a rational power. And so we were able to prove that it's Benford if and only if Y is irrational. And so in the interest of time, I'll just talk about what happens if Y is rational, and I'll just say a few very brief words about what goes on if Y is irrational. So if Y is rational, let's say it's R over Q, what we see is that every time we increase J by Q, we've just padded a bunch of zeros. We've just padded 10 to the R to our number. So if we want to look at what is the probability of being in that congruence class, in that equivalence class, it would be N over J, N choose J plus N choose J plus Q plus N choose J plus 2Q, and so on and so on and so on. And there's a couple of ways to handle this. One is there's actually some formulas that tell you what these sums are. And if you know these formulas, you can do it very easily. The other way is to say, well, if I change this from J to J minus 1 or J plus 1, how much am I changing things by? Do all of these sums have approximately the same value? Do I have approximately a uniform distribution of probability among the Q congruence classes? And the answer is yes, because if we shift the J down by 1, then you can see, okay, well, this dominates that one. But then if I throw away the first term of this one and I can compare to the next sequence, one shifted higher, we'll see we'll get an upper bound modulo that first term. So you can show that really up to 1 or 2 binomial coefficients, these sums are all approximately the same. And then since they're all the same, that gives you the uniform distribution. It's a bit more work if Y is not a rational number. What you would do is you would still have a geometric process, and then what you would do is you would look at the Gaussian and say, well, most of my probability is within that Gaussian, and then try to do some things. If I'm looking at things, can I maybe approximate the Gaussian, some kind of uniform approximation? And that can be done. Just some data to just show you how bad things can be. If P equals 3 over 11, we end up getting an irrational number, and it's not so bad for Benford. But if we take, as I said, 1 over 11, everything is going to have the same value. A little bit more fun, I chose the probability to be 1 divided by 1 plus 10 to the 33 over 10. And again, you can see very non-Benford behavior. If you do the random cuts, as I said, the analysis is a little bit more complicated. It turns out to involve products of random variables being Benford, and there are some slides at the end if you're interested where you can look at stuff like that. All right, so just a few brief conclusions. You can see that many different systems exhibit Benford behavior. And there's a couple of reasons for this. And part of this is because the same math describes so many different things. Difference equations describe so many things. Products of random variables describe so many things. The key ingredients of the proofs are logarithms and equidistribution. So there really is no bias if we look at it on a log scale mod 1, but we don't really want to look at our data that way. And then the last is applications to fraud or data integrity. So this has been used to detect fraud all over the place. In addition to financial transactions, you can use stuff like this to detect, has an image been modified? This is one way that a lot of communication happens where you do not want to risk sending a message where the recipient could then be detected receiving the message. You can post something on the web, and if somebody downloads the image, if they know how to remove it, they can actually cull out the message. It's been used to detect fraud in voting, in trying to look at the distribution. There are people who have tried to use it to detect fraud in scientific papers. Is someone making up their data? Sometimes it is very easy to tell when someone has made up their data. There's been several cases where a researcher has studied very different phenomena, but interestingly has had the same graph, the exact same graph and the exact same data set for very different phenomena, where they're just cutting and pasting their data. And so if you're lucky enough for someone to do fraud like that, you don't really need a powerful test to prove that something is happening. The more challenging case is when we don't know if Benford's law should be true. And so I was contacted by some researchers in Europe a few years ago, where they thought that there was some data in some of these protein databases where they thought people were just making up some numbers. And could you tell this by looking at Benford tests? And the problem is we don't have any reason to believe that the data necessarily should follow Benford's law. So thank you. If there are any questions, happy to chat.
Thank you very much, Stephen, for a wonderful talk. So any questions for Stephen? Questions? Oh, Jennifer, you're on mute.
You hear me now?
Yes.
Yes.
Okay, sorry about that. What happens if you're working in a base different than 10?
So a lot of it will depend on what you're looking at. And so if you are looking at, if you look at this base 2, you do not expect to see Benford, you'll see just everything will have a first digit of 1. If you look at things base 4, you would not expect to see Benford of 2 to the n base 4, because the log of 2 base 4 is now 1/2, and that's a rational number. So the Benfordness of something could change depending on what base you are using.
Right.
Now, something like the Riemann zeta function is beautiful because that should be Benford to every base.
Nice. Okay.
Another thing that might be interesting to look at is some continued fractions, where there is no natural base lurking there.
Thank you.
Galen?
Yeah, so when you're talking about stick decomposition, it reminded me of the Cantor set. Do you know if there's something sort of Benfordian about the Cantor set with splitting up an interval into thirds and thirds and thirds?
For years, I've been dying for someone to work on like a Mandelbrot set or like a Newton polynomial with me. So if you have any interest, please email me. It's fascinating to look at what's going on in terms of like the number of petals or whatnot, in terms of what formulas do we have.
Yeah, maybe also L systems. Maybe there's something Benfordian about how some of them grow as well.
Right. And again, part of it is just certain natural processes, certain power relations are going to be Benford. And so if you have enough things going on, it's not unreasonable for that to emerge.
Yeah, that's interesting. Thank you.
Yep.
Andy, I think Andy has had his hand raised.
Yes, hi. I'm actually an applied mathematician. I work in numerical methods and scientific computing. So I'm not, in this area, but I find it interesting that you talked about, image sort of detection and fraud. So I was wondering, with the recent developments in, deep learning, and they have, people worry about deep fake and all these things. Do you think you can apply the Benford to kind of detect deep fake images that have been generated? Do you think there's something that you can detect using Benford tests?
Is this to detect whether or not an image is a real image or a doctored image?
Yes, like generated through a deep neural network or something like that.
Yes. I think there's a good chance that you can detect. I know doctored images have been detected. And so if the entire thing is constructed, it would be interesting as to, is something missing there? And again, a lot of times it's not exactly Benford's law, it's something else that goes on. But there are ways to modify Benford, to generalize it, to have related distributions where you can see something has happened. That's interesting because well, I'm starting in this field, and it's apparently a very difficult problem. It's like detecting a virus, computer virus. It's always kind of who has the upper hand, and
I think maybe if someone looked at this, maybe it'd be interesting to see if you can use this in a detect deepfake using Benford law.
Yeah, I actually just heard a talk earlier today on how big data can mislead you, and how a lot of the classifiers sometimes have very bad mistakes in terms of classifying some people as animals or things like that. And I know there's a lot of concern as to, is it actually a human being who is trying to log onto this website? So I'm going to show you 9 pictures and click all the ones that have the stop sign or whatnot. And so these are being used more and more often. Images like this are being used for passwords in some companies.
Thank you.
Yep.
Any more questions?
I have a question. I think like this difference between E and pi, I guess it's related to irrationality measure of these numbers, right?
Yes.
Yes.
Yes. And let me see,
And it's higher irrationality measure for pi, and E is relatively not so big. 2, I think. Okay, thank you.
so
Any other questions?
I have another one,
Yes, go ahead.
if I may.
Yes, of course.
So can we use this to detect cheating in our first year calculus classes?
I mean, I remember my first calculus class in college, you could replace all of the integers with Roman numerals, and we saw so few integers, it wouldn't make a difference. So what kind of answers are you getting?
Well, I don't know, like, how could we design a test for a first year calculus class so that we could, in fact, detect cheating?
Right. I mean, the real cheating would be, I think, people looking up answers or collaborating with each other. I mean, that's what you're afraid of. It's not going to be. Yeah, I mean, one thing I've done when I used to write problems for, high school math competitions is, if you give people, 5 choices, A, B, C, D, E, a lot of times you can just look at them and you can see which answers are probably absurd and should be thrown out, and which ones are all somewhat close to each other, so one of them is probably right. So what I would often do is I would say, add the digits in the odd spots and subtract the digits in the even spot. What number do you get? And then list something like that to try to apply some function to the answer to try to mix it up a little bit. And so if people are just randomly guessing, or if the answers are random, you would have some kind of nice distribution.
Right.
And so the only way I think would be, I know in probability, it is a requirement, and if you don't do this, you don't get to go to mathematical heaven, that you have to split the class into 2, and one class flips the equivalent of a penny 100 times and records, how many heads and tails and what the string is, and then the other half just makes it up. And as the professor, you're supposed to be able to tell. Most students know to have about 50-50 split with heads and tails, but they don't know what the length of the longest run should be. And the length of the longest run, what is the probability of having a run of length 4, 5, 6, or 7? The answer to that is actually a nice difference equation, which is a generalization of the Fibonacci numbers. And so you would need to put something like this into the exam where the students would not know what to do.
Yeah. Okay, thank you.
Yep.
I think Galen has another question.
Yeah, this is kind of an open-ended question related to Benford's law, which I was thinking of, like scale-free networks that have sort of a preferential attachment of the more connected you are, even more so you'll be connected in the future. So thinking about graphs that are like randomly growing according to a distribution, Can you think of applications to looking at whether the growth of a network is Benfordian or Benford?
I mean, to some extent, that's a quick test to see, is it plausible that it's growing exponentially? But, you know, to me, it would be, I guess, more just, can you actually trust the data that's coming out? And so, for instance, in America right now, are we being recorded or are we not being recorded right now?
We
I
are.
need to know how to phrase things.
I
We're being
stop.
recorded, okay. So I will phrase things then very diplomatically. Certain major big tech firms, all hail big tech firms, love you, have been found to be playing games with their search algorithms and have massively changed how certain websites are being found. And in fact, some news sites have said that their hits have gone down 99%. And in fact, their stories, even if you put in the exact title with their name, it's not being found from them. It's being found from a third-party site that's illegally posting. And so there could be some interesting stuff that could be done looking at hits that are happening with certain key phrases and trying to see, is it a true random search or is something going on and are people playing some game in terms of trying to hide certain websites? And so to me, the question is always, can we use this to try to find some type of fraud?
I have a question actually. So for
Yes.
For the Riemann zeta function, actually the
Yes.
slide is there. So you showed us, you said that the data shows that zeta at half plus k, ik over 4, as k varies over, k varies over the integers?
Yes.
Was it? Yeah, so that follows Benford's law. Now, what other families of functions can you do that for? And can you get some more, in a sense, effective results like the results you have and the results of Ligarius and sound for the 3x+1 sequence?
Yes, and so let's see. So I'm just trying to see how much detail is in this slide. Okay, so let me switch to a different set of slides. And actually, so just as I'm talking, to answer a previous question, the irrationality exponent that came into play for the 3x+1 problem is I had to show for quantified equidistribution that the log of base 10 was a finite type with its irrationality exponent. And just doing the most crude bound possible, I get, you know, basically 10 to the 602, which is the largest finite number I have meaningfully used in any of my stuff. So let's see. This one, oh wait, this one would not have it. Oh, yeah, so we say an L function is good if it satisfies the following wish list of properties. So it should have an Euler product, it should have a meromorphic continuation, it should have a functional equation. So far, this is not controversial. I think everybody's willing to say, if I'm looking at an L function, it's got to have these. Next is some statement about the sum of, you know, the modulus squared of the coefficients, just, you know, some growth rate, that they are basically the monogon, you know, that they're at most 1. And then we have some control over the number of zeros. And so this is the, I think these are called like the density theorems. One of my advisors, Henrik Ivanitz, basically said, we believe the Riemann hypothesis that all the non-trivial zeros have real part 1/2. This is counting how many do you have off the half line up to height t. You are trying to get better and better estimates for the cardinality of the empty set. So, you know, we can show the empty set has at most this many elements. And so as long as you have control like this, then you're fine. And you can do the analysis. It basically comes down to the log normal law. And so the log normal law basically says that the log of the absolute value of the L function converges to being normally distributed with some error. And then we just need to have control over everything. It's actually not that bad. When I was doing this project with Alex Kontorovich years ago, I took the L functions and he took 3x plus 1 because he did 3x senior thesis.